Alrighty, I think we're good here then to get going. Again, this week, not exciting. I apologize. Array-based sequences are lists in Python. Python does them already for us, and they just work out beautifully. You've got to go through some hoops to make these things work in other languages. So we're going to look at all the hoops. We're going to pretend like lists don't do what lists do, and then we'll build one from scratch. Seems a little silly, but again, the idea is we're going to look at what is fast and what is slow about this particular way of storing data. And it applies to lists. Lists are fast at some things and slow at some things, but having built one from scratch, hopefully you get to appreciate why it's fast and why it's slow. And that's sort of the idea here. And that's why we're going to build all of these from scratch. They all exist. We have libraries for all of them. Like, smart people have done them and made them as fast as they can be. But we want to spend some time looking at why are they fast and what are they fast at and those sorts of things. So stacks, queues, and decks are much more interesting than array-based sequences. Linked lists are much more interesting. Again, building them from scratch is kind of fun for some of them. But just pretend like you don't know what Python lists are for now. Is that okay? We'll just pretend like we've never heard of them, and then we'll go from there. So let me fire up PyCharm. Oh, you got this already. I did put this code out on GitHub. So again, we need this position class for lab 3. It doesn't have to be a class, but again, thinking about object-oriented programming and the way we know objects work, and we know if we can override this less than thing, it just sorts really easily. This works well. It's an option. Again, you don't have to do it. Like, anything we do with object-oriented programming can be done without object-oriented programming. But it lets us think about it and talk about it and plan it and design it in a way that's a little bit more natural. Like, oh, hey, I'm going to make a list of positions. Okay, and what is a position? Well, position is a row and a column. Here's the position on the chessboard. And what do I do with it? Well, I can figure how many more moves I have. Okay, cool. And then when I sort, I want to see who has the least number of moves. What is less than someone who has more moves? That's all. So using that here lets us plug that into a Knight's Tour solution, using that backtracking. Hey, I'm going to try it. I'm going to try it. I'm going to try it. If I get stuck, just come back, try the next one. If I get stuck, come back, try the next one. That sort of approach in recursion here. Not particularly fast. In fact, it's slow because it literally tries every single possibility. But it's a very simple, easy to implement recursive solution here. Later on, you can learn about fast pathfinding and things like that. I think they still do that in the Intro to AI class. That's one of the traditional learning a little bit more about AI is pathfinding, and then fast ways to do pathfinding and things like that is kind of fun. So good things there. So we start a new project. This is week 4, array-based sequences. And we'll put it in this window. So we can close the other one. All right, this one over here. Let me get rid of that garbage. So the basic idea with an array-based sequence is we are asking the operating system for a chunk of memory that's contiguous to store a bunch of things. And why it has to be contiguous is because we look things up by index. Hey, what's at index 27? Well, to get to index 27, I'm going to take where it started in memory and go out 27 spaces and find what's there, right? No matter if I have 27 things, 27,000 things, a gazillion things, to find a given index is just one mathematical operation. Your index number times your size. Just offset that, go read the memory. So it's really quick at grabbing any individual item out. That's what lists do for us, right? We can grab stuff by index. So array-based sequences, because they need to have contiguous blocks of memory, have to work in a certain way, right? So if I say, hey, I wanted my numbers to be 1, 2, 3, 4, 5. Sure. Python's going to go allocate, ask the operating system for room to store a bunch of things. Now, there's some fun stuff we can do in Python. Is it like size of or something? I think it's, Python size of objects. Let me see what this is here. It's probably in the textbook too, and I just forgot. Oh, sys.getSizeOf, that's right. So if we import the sys library, so if we import sys, and then we can say print size of numbers is sys.sizeOf, get size of, there we go. Get size of, really? Oh yeah, it is get size, okay. I just forgot the word get size of numbers here. So we can see how large this is. Well, that's about 104 probably bytes. Is that what it says? Is this bytes? returns the size of the object in bytes. So 104 bytes of memory are being used to store this. Sure. And I take numbers and we append, I don't know, let's add 6 to it. And let's get the size of numbers. Still 104. Well, that's kind of fun. It's the same size, but it has more information in it now. How does that work? Well, because Python knows that lists are mutable and they can increase and decrease, it over-allocates. It says, oh, you want to put 5 things out here? I'm going to give you space for more than 5 because you're probably going to add to it. And if I had to go get more space every time you added another number, it's going to be really slow. Because what has to happen is to get new space in memory that's contiguous, you can't just add on to the end of wherever this is in memory. Because it's not guaranteed that that next block is going to be free. The operating system doesn't work like that. So to make more room, you have to say, hey, operating system, I need a big block of memory here. And it says, oh, here's your big block over this way. Yeah, you were over here, here's your bigger block over this way. And we have to copy each item. Here's number 1 to number 1, number 2 to number 2, number 3 to number 3, number 4 to number 4, over to that new space. So the more things we have in my list here, the more things I have to copy. Again, we talked real briefly about how fast things are, that complexity, right? There's time complexity and space complexity. You can read the whole chapter if you want. It's a big snooze. You'll probably read it next semester in 350. I guess skim it, I don't know. It's very dull. But the more n things we have, the more n time it takes. Because I have to copy these many things. So if I have to copy n items every time I add one thing, it's going to be terribly inefficient. So the fine folks at Python and the smart computer science people that are our predecessors said, why don't I leave more than one extra space for you? So you can add a couple things, and then at some point, I'll go make more room and copy things over. So there's a really cool, I think I can just draw it here. Let's see, in Word, which is fun. So if you imagine we have a little graph here. Is that a little graph? So this is the n items, and this is the operations. This I should have just written here, but I was committed to using the little drawing tool here. So n items across the x-axis, operations, and the y-axis here. So if I'm oversizing my list here, and I've got room for 10 things here, to add item number 1 here is 1 operation. Add item number 2, 1 operation. Add item number 3, 1 operation. Item number 4, 1 operation. Item number 5, 1 operate, right? If I've got room for it, it just throws it down to the end. Nothing has to happen. Eventually, I'll hit that space where there's no more room. I don't have room to put something in here, right? This was 10 or whatever it happened to be here, right? What has to happen then is we say, hey, operating system, give me more space and copy over all the previous things. So the number of operations that it's going to take is n operations, right? That 10 in that case. So in this instance here, we now have 10 operations. Then we can go add a bunch more, right? We made extra space, right? So then the next add 11 is 1 operation, add 12 is 1 operation, add 13, 1 operation, on and on and on. So if every 10 we increase our space by 10, then the next one then is going to be 20, and then at 30 we'll be at 30, and then at 40 we'll be at 40. See, this isn't going to be very efficient. So the fine folks who studied this sort of thing said, hey, you know what would be better is if every time we just double, we do a geometric progression. So if I had 10, I'll double to 20. If I had 20, I'll double to 40. If I had 40, I'll double to 80. If I had 80, I'll double to 160. Because what that lets us do is say we're spacing out the distance in which it will take n operations. So now I don't just get space for 10 more, I get space for 20 more. And then it'll take me 40 operations. What we get to do with that then is you essentially get to take this bar and lay it down this direction on average. And we take this bar, we say, hey, lay it down this direction. So on average, it's going to take me 2 operations. Most of the time it's 1. Every doubling, it's n. But if you average that out, or amortize is our fancy word for that, the amortized average is still just 2 operations, which is constant. Because I've made room for double the amount that you just added. So we can say, oh, you know, it took me 20 operations here, but now I have room for 20 more. So it's as if for the next 20 adds, that 20 operations I just did is averaged across your next 20 for an average of 2. So adding to an array-based list that does this geometric doubling here is a constant time. So that's on average, right? So we have this big O notation. We say that the O of this, right, the average time is what we typically care about. And if it's constant, is just 1. Thanks to some fancy math waving, you essentially get to throw away constants. It doesn't exactly work like that, but the difference between 3n and n squared really is just n to n squared, right? We can essentially throw away the constants. It's some fancy math hand waving. The book will take you through all of it, but essentially any constants just we boil down to 1. So it doesn't matter if it's like 3n, well really that's just n. We'll just say, oh, forget the 3, it's just n operations, because it grows linearly. Even if it's a 3n or a 0.5n or whatever, it's still linear growth, this sort of thing here with this. So for adding an item, ADD, there we go, it's constant, right? Because we're going to amortize that average across. Now with Python lists, we can remove items. Right? We can say, hey, I want to remove a value or remove at a given index here. Well, how long is that going to take, right, to remove? So we say our remove is what has to happen if we take out the thing at index 3. Right? Everything after it has to get shifted down so there's no gap at 3. We can't not have something in index 3. So index 4 shifts to 3, 5 shifts to 4, 6 shifts to 5, on and on and on. So the n items we have all get shifted. So the technical term for that, you know, if we're removing the k index, I don't know why they use k, but sure, the kth index here is going to be n minus k, right? If k is 0, we remove the first thing, we have to move n items. If we remove the last thing, right, then k is n, it's 1 operation. But, again, thanks to our fancy hand waving here, k is technically a constant, right? It doesn't grow in terms of n here. It's not like any sort of relation here. So removing, we just say, is O of n. The bigger it is, the longer it takes to remove something, because you have to do some shifting. You know, if we were to average that out of n minus k across all the different k's, you'd come up to like 0.5n, right? And we just remove the 0.5 because that's a constant. That's how that math works with the n minus k. So adding is really fast, removing is really slow, right? How about finding a particular item, right? If we just wanted to say, hey, does it contain, or is it in, like our in operator, right? A find or contains, we'll just call it find. Is it okay if I say find? I don't think find is technically in Python, but that's probably okay. If I say, hey, do you have the number 27 in your list? Well, I'm going to go look at the first item, and look at the second item, and look at the third item, and look at the fourth item, and look at the fifth item, until I either find it, or I've read every single n item and didn't find it here. So, again, it's fancy hand math waving. It's like n minus k, where k is the index of the thing you're finding. But on average, it's beginning, the middle, the end. On average, it's probably in the middle. So half of n, and we just throw away the constant. So it's still n. So finding is still linear, right? The more n I have, the longer it's going to take me to find something. I think that makes sense, right? We have to look at all your items and find it. So it's really good at add, right? Constant is really good. That's fast. I could have a million things and it's still 2 operations, right? Constant number of operations to add something on average. Technically, some of these things are really slow. So there's O is like our average time. There's also like a theta and an omega. We use all sorts of weird letters here for reasons that I don't care about. Worst case performance is generally good to know, right? What's the worst possible speed this could happen in? And our worst case, right, is definitely going to be n, because I have to copy n items. I hit the point where I'm out of room, I have to double. Now it's going to be slow. So worst case is good to know. You know, most of the time though, we only really care about the average. Because if on average it's fast, I'm happy, right? Because most of the time it'll be fast. Life is good. And we've averaged that out here. So average is the important one for us to focus on. And then best case performance is like ridiculous, because you're never going to get best case. So we don't bother tracking it, or I don't care about it here. It's not a practical thing to even measure. Like, I don't care if it's this fast in its best case. I care about how fast it is on average, because that's most of the time when I use it, it's its average. But you can track best case, average time, and worst case performance across the three measures. We'll just focus on big O, our average case, the entire time. Occasionally we'll look at worst case, because it's nice to know. And I will probably never mention best case again. So how do we do that, right? The Python list does it for us here. So why don't we go add a bunch more numbers here? So let's go append a bunch of numbers and get the size here again. So let's say, actually, let's do this. Let's start off with an empty list here, and we'll print the size of numbers, and then we'll say for, I don't know, number in range. Let's go like 1,000 here. Let's go take our numbers list, numbers, and append the number here, and then see what size it is here. So this will be, here's our number, colon, and then size of numbers, right? So with one item, or 0 items, right? We'll start at 1 here, because that'll be a little bit nicer. So with 1 item, what's its size? With 2 items, what's its size? With 3 items, what's its size? On and on and on. And we're gonna see, oh, that's a lot of scrolling here, goodness. 1,000 might have been too much here, right? All right, we start off with room for a couple here. It starts with nothing, actually. That's interesting here. And then the next couple, we're at 88, and then we're at 120, and then we're at 184 for longer. We're at 248 for longer. I don't remember the actual math behind how Python does this, but it's fast, right? Whatever the actual arithmetic is, really smart people have looked at it and said it's really good, but we'll see it grow. It's not going to look like it's exactly doubling. Don't sweat it. There's other things you can optimize at some point with small numbers here where the math works out differently. That's all beyond me, to be honest. I don't care. We'll just assume the doubling is the right thing to do and call it good enough. Is that okay? All right. So it's not exactly doubling at this moment here, but you'll see each one is generally a little longer than the next one here. Right? We're at 920 for a while, then we're at 1080 for longer, and we're at 1240 for even longer. And as we go, right, we'll stay at given sizes for longer. So all this means is Python said, hey, I need more space than what I'm actually storing. Right? Because I know I want to make adds fast. I want to make append work quickly on average. So give me more space, and then Python manages that for us. When it runs out of space, it'll say, oh, hey, operating system, give me some more space here, and then it'll go and allocate more space. Right? It just says, hey, operating system, give it to me. So if we didn't know how this worked, we could do it ourselves. Right? If we pretend like there was no append function to lists, if we said, here's a list and its size is 5, and it is fixed. So in other languages, they call that an array. Arrays are fixed size. You can't append to basic arrays in other languages. Again, Python has lists. We're just going to pretend like it doesn't work anymore, okay? We write our own. So what we need to do is we're going to go add a class. So here's our, I don't know, array-based sequence. Sure. And this will be a class for array-based sequence here. It'll have an init method here. Now, you probably don't need to tell it anything here to make an array-based sequence. Again, we'll assume we start empty, and then we'll go figure out how we can go append to it here. So what we need to do is we need to make some internal storage for our data, whatever we're storing, right? So under data, I think the book calls it data. I forget now because I haven't looked at the chapter in a while. I'm doing this off the top of my head, which is probably a mistake. Well, we're going to go with it. It might be fun. Honestly, I like showing you guys when I screw up. I don't know if you think that's as interesting, but it's a very good representation of what I did, and I got paid a lot of money in the real world to do, so I think it's fair to show you that. Is that okay? All right, so we're going to make a list here. Now, we want to oversize this list here. Right? So we want to have some sort of default size that we're going to start with, and what we're going to do is we're going to put a bunch of nones in here. So none means nothing. It's null, it's empty, but it's going to have room to store that emptiness here. So let's go with like, I don't know, how about 5? 5 seems reasonable here, okay? Then we need to track our number of items. So the actual number of items that we're storing in our array here, and then we're going to track our current size. Well, the current size is easy to track because we can ask for the length of data. Right? We don't really need that here, so we just have our number of items here, okay? So what we can do then, we can add a definition for length, right? If you want to get the length of an array-based sequence, we're just going to return self.number of items, right? Hey, I'll tell you how many items I'm storing, right? That's my internal tracking here. Then what I can do to define my own append method, given some, I don't know, the item to append, is it item fine here for the name? We're going to take our, first we need to look, do we have space? Okay, that's an important one. So we're going to check to see, sorry, let me scroll down a little bit here. If my self.number of items is less than the length of self.data. So if I have 5 items, right, index 0, index 1, index 2, index 3, index 4, is 5 less than the length of this? Well, 5 is not less than 5. We're out of space. 5 equals 5. There's no room here. So if we don't have room, then let's just leave it to do add more space. Well, you know what? Let's just do this. We'll just say self.add space. Right? Well, pretend there's a function here called add space here. And we can even go add that in here, right? Let's define add space here. Now it's not going to do anything yet, right? So this one will leave the to do. This, I don't know, to do something. Fix me, finish it, whatever here. So if there's no room, let's go add space. Great, done. After we've checked to see if we have space, I can go add that item. So I'll take my self.data at the index of self.number of items, and I'll assign it the item. Right? Hey, when I have 0 items, I'm going to put something at index 0. Right? When I have 5 items, I'm going to put something at index 5, because 0, 1, 2, 3, 4 are the first 5. Right? So 5 is the next open index here. So my number of items is the next open index here. So I'll take that item, we'll assign it, and then I'll take my self.number of items, and we'll add 1 to it. Right? We just added an item, count it. We added 1. Excuse me. Right? So that's how we can append. Right? Find the next open space, drop it in. Again, we'll get to the resizing later. Add space, whatever here. That makes sense? Right? So we can append. Right? If we wanted to, let's see, we wanted to go remove something, right? Remove a given item. Again, we'll remove by value. We don't worry about removing by index. We could always add that in later here. But to remove by item, we're going to loop through and try and find it here, right? So we have to go find the index in which this item is here. Okay, so we need for index in range the self.number of items. And I don't need to go over the length of data. I only need to go over the number of items, because that's the only place I actually care if there's something there. Right? There should be nones in the rest of it here, and I just do a bunch of extra work, and I don't need to. Right? So just however many items I have for that index, let's go look. We can say, hey, if self.data at the index is equal to the item, now we need to remove it. Right? We're going to get rid of this one here because we found it. Great. If we didn't find it, we'll just keep on going. So what do we have to do to remove? Well, to remove it, we need to shift everything back down by 1 here into its spot here. Now, this gets a little messy here, but it's doable, right? So it's going to look a little weird. So once we find it, then now we're going to do another loop and shift everything down, right? So we're going to say for index in range, now from the index here, right, we want to start shifting down, but actually really the index plus 1, I want to take the next thing and move it into my spot here. So really index plus 1 up until self.number of items here. We're going to go do something. I'm sorry, this is, I don't know, index to shift. How about that? Some people really like putting the letter J here in their inner loops. I would strongly encourage you to never use J, because I hate it. Because when you look at an I and you look at a J, I get confused really easy. I'm not the sharpest tool in the shed, and I'm just going to get confused. Like, well, which one is it? Because one just has like a little curl at the bottom. I hate it, and I like really long names here. It's nice and meaningful. I don't never type the whole thing anyway, right? So I'm still being lazy. All right, so once we found it, now we need to start shifting. So starting at the plus 1 up until the end here, let's go shift a bunch of things down, right? So I'm going to take self.data at the index, index to shift, minus 1 equals the self.data at the index to shift, right? So for every index I'm going to shift, move it back 1, 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 right? That's it. That's all I have to do. When I'm done with that, then still inside my if loop, if block here, I want to break this outer loop. Stop running the for loop, right? Because I don't want to go try and find another item, right? We only remove the first occurrence here, right? Cool. Once we've done that, then, I'm sorry, actually before we break, we should take our self.number of items and minus 1, right? We successfully found it and removed it. We now have one less item that we're storing, right? Now we can break. If we went through that whole loop and we didn't break, now remember you can use that fun little else in a loop here. We could raise an exception if we wanted to. That's probably, I don't know, raise item not found, there's like a not found, sure. I don't know if that's the right one here. We'll just say value error. I like value errors. Value error, item not found, something like that. So if we didn't break and we looked at every single item in the number of items that we have, let's raise an exception and say, hey, you tried to remove something that didn't exist, dummy. Go fix it or crash. Right? Exceptions are nice because they make people deal with it here. Excuse me. So we should be able to append something here, and then again on average we're looking at O of 1 constant here, because if we do our geometric doubling, we'll average that cost out, the time out across all the next n operations, right, that we had to double for. We get our constant time on average. Worst case, it does have to double. We have to move n things, right? But again, we don't particularly care too much about worst case. And then remove, right? We said this one was O of n, is n minus k when you average that out is half of n, and half of n is still n. So sure, the more n items you have, the longer it takes to remove something, because you have to shift everything down. I think that one makes a lot of sense if we think about it here. Okay. The next one we were going to do was what? Find. Do we like calling it find? Is that fine? To find an item. And really, it's just this loop here. What do we do? Return the index, I think, when you call find. Or that was index of or something? I forget here. And then otherwise, we can return -1. I think that, does that one sound familiar? If we didn't find it, I don't know if we had to raise an exception, or maybe we just say, hey, not in this list, here's an invalid index. That's an option here. Depends on how you want to write that one here. And again, this one is O of n here. We have to go look at n items, or n minus k, where k is the index of the item we actually had, and that averages out to half. We throw away constants. It's really fun to be able to throw away constants. I don't know, kind of like Calc 2. You get to throw away your constant, right? Your plus c, just forget about it. Like, nobody actually cares about the c, but some people really do care. I don't know how that all works. Your math is crazy. I feel like it's really theoretical at some point. I like tangible, hands-on stuff I can really make sense of. So, all right, so we've got our array-based list here. Now we haven't figured out the resizing, so let's do that. So to add space, we need to go double, right? So when we're adding space, we're going to make a new array here. So we want new data equals a list here. Now, getting none, 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 none is a little awkward here. So what you can do, I'm pretty sure this is the right syntax. We say none times, we want self.number of items times 2. And let's force that order of operations. I think that matters. I'm not really sure. Probably will work either way. That's probably redundant, but that's fine. Nothing wrong with putting it in parentheses, right? So now this will be none times the size of however many items we had doubled. So I'll have room for 10 things, or I'll have room for 20 things, or 40 things, or 80 things, or 160 things, or 320 things, or 640 things, and on and on and on and on. Okay, then we need to go through and copy them, right? So for index in range self.number of items, we're going to take new data at the index equals self.data at the index, right? Go from the old one into the new one, 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 for every item we have, right? When we're done, then we can say self.data equals the new data, right? Get rid of this old one here. You now are the new one. Right? Here's the new list I just created in memory. Boom, we've added space, we've doubled, right? And again, this one, on average is still going to be n things, because we're always doubling. It's always n, right? Worst case is n, best case is n, average case is n. It's just always n here, right? So sure, O of n, right? It takes this much always to add more space, because we're just doubling here. But because we get constant here, because it's on average, because we doubled, we get the next n across, right? We get to average that out. That would make sense. Do we need to look at the math for that? It's in the book. Was it? Goodness. What was? It's like n minus 1 times. No, it's not even that, right? We don't get any n squared. I forget how it works. I drew the picture. It's probably close enough. We can look at the book for the math later. But because we're doubling, we've got room for the next 20 to happen in constant time. And then we double again, we have room for the next 40 to happen in constant time, right? Drawing the picture and laying the bars down helps, I think. All right. So now, essentially, we've built out a Python list without ever using the append method that Python knows how to do, right? If we pretend like lists can't append and they're in fixed size, we've now solved for that, right? So now I can go use my array-based sequence here. So we'll make I'll go import that. So from array-based sequence, import array-based sequence, and we'll go make one. So here's my sequence is an array-based sequence. And then, I don't know, for number in range 100, let's take my sequence and we'll append the number. Now, I don't actually have a way to get any of these out, which is a little bit unfortunate here. So it'd be nice if we could get them back out, right? So we can define, was it index? I think it's index of self. Is that? That's not it. Might have to go look that one up here. It's not item, iter, get, shoot. Oh, it's one of these double ones here. Which one is it? You have to Google it. Is it get? No. All right, I'm just gonna go Google it here. Python override getting item by index from object. Yeah, get item, right? No, not allowed. Get item. All right, maybe this is not helping here. Get item. Should we look at the textbook here? Get item. What does this one do? Get item. Yeah, it allows you to use the index operator. Okay, I thought it was get item. Get item. Okay, let's try it. Let's try it. Get item. Get item. This should be index then, right? So given an index here. So return self.data at the index. Now, we probably need to check this though, right? Because we oversized, if you ask for an index that's invalid, but still within my actual oversized list, I'm going to give you back none, and that's not proper, right? So we want to check. So we're going to make sure if my, 0 is less than or equal to index is less than the self.number of items. Right, that should be the range of valid items. We'll raise a index error, invalid index, right? I think that's a nice built-in one. Otherwise, we can return the data, right? There we go. And then we should be able to say for index in range, length of sequence, right? Because we have a length function, we can return the length. Hey, I should have 100 things. We added 100 things. We should be able to go return or print them all out. So print the sequence at the index. Right? We just added the get item. That should work for our square bases here. Oh, we're so close. We're so close. Let's see. So when we appended here, list assignment index out of range, self.number of items equals the item. Let's see, okay. Let's put a breakpoint in. I don't know where it stopped. Let's try it. We're on a debug mode. All right, so we're checking. Right now we have no items, and the length of self-data should be 5. Cool, length is 5. Did we just add space? I don't think we had to add space. Oh my goodness. This is wrong here. You let me do a bad thing, folks. Right? The number of items should always be less than the length here, right? Because we've oversized. This should be the opposite. This should be greater than or equal to, or really equals. Is probably the only thing we care about, but greater than is probably fine, right? If I added my 5th thing and I only have room for 5, if I'm at my capacity or over, we can't actually add over, but that's fine. Then we need to go add space. That ought to take care of it here, because we were adding space every single time. Was doing something super weird here. I don't know what happened, but let's try that. Oh goodness, invalid index. Okay, well that's on get item. All right, we're getting closer then, right? It probably went and added all of them. Let's put a breakpoint here. Oh, I don't want this one here. Let's continue. Right, so we got through. Here's our sequence, right? And our sequence has a private data. Look at that, with all my numbers in it. Looking pretty good so far. Number of items is 100. Should be good so far. So where is it failing? Printing out my invalid index then. So let's step into our code here. Right, to go into our function. Now we're checking our index, right? 0 should be fine. Again, you let me do a bad thing, folks. Come on, work with me here. This is the valid range, not the invalid range. I was just checking to make sure you guys are paying attention, right? Obviously. No. That's the valid range here. If it's not valid, we'll raise the index error, right? These ones are good. You should have something here, right? All right, it's 2 in a row, right? Third time's got to be the charm, right? Hey, it worked. Okay, that was exciting. Very, very exciting. Cool. Right, so we can get things out. All right, what else can we do? Right, there's a get item. How about a set item? Given an index, right, and the item. So again, make sure the index is valid here. Now, I feel a little bad having this and having to copy paste here. And anytime you have the same code twice, you should feel bad about yourself. That's a good feeling, right? Make sure you're a better developer. So let's fix this, right? So really what we want is like not this, and then we can return that error here. If it's not all of that here, sure, like that's one way, sure. We can check that. Then if we're going to do something more than once here, let's turn it into a function. So PyCharm knows how to do that. Right? So it's a nice built-in handy thing here. So you can right click and you can say refactor and extract method here. So let's call this, I don't know, check for valid index. Okay, so now we have a check for valid index. Oh, that should have been private here. Oops, that's okay. Private. You don't need that to be a public function. So we'll go check if it's a valid index. If it's not good, we raise an error. If not, nothing happens. Right? So now I can use my check for valid index on set item. And now I don't have the same code twice and I feel better about myself. So if it's invalid, we raise the exception, we stop, nothing else happens. Otherwise, we're going to say here's the old item is self.data at the index, and then we'll take self.data at the index, assign it the new item here, and then we'll return the old item. It's kind of fancy to return it here. I don't know if anyone actually cares, but that way they can get that value back out. Give them one last chance to get it in case they forgot to go get it first. Or we just go set it. Either way is probably fine here. Not a big deal. And set doesn't change the number of items that we have. Right? So we're not changing our number of items at all. We're just saying, okay, I can go set something at a given index here. So now I should be able to go and use that sequence notation and say, hey, here's my the index notation, you know, at 10 equals 100 here. Let's go do that before we go print them all, right? So we should get 100 in here. Look at that, we got 100 in here because we went and set the value at a given index. We added in some new functionality here. Right? Again, a lot of work to make a Python list. I get it, I'm sorry. It's a little silly. But we want to look at why are these things fast? Why are these things slow? So how fast is it to set an item, right, on average? Is it going to be a constant time? Is it going to be based on the number of n items I have? How long does it take?
Based on the items you have,
So the more items I have, the longer this is going to take?
I think.
So if I have to set, if I've got 100 items and I want to set item 27, is it going to take 100 operations?
No, you shouldn't have to reset everything else.
No, right? This same 4 lines of code, nothing has, there's no loop here. So if you look at it and it's not looping over your items, it's definitely not O of n, because it just does 4 things. And again, we throw away constants, so 4 becomes 1. We say this is O of 1, right? Setting is O of 1. How about get here?
Same thing, it's not a loop.
Yeah, O of 1, it's not a loop. Sure, we're good. And okay, sure, there's like one more line of code that technically runs here, but again, it's not a loop. Right? If we're not looping over items, it doesn't matter how many items I have. That's our first look here, our first clue there for how fast these things are going to be here. So we can get, we can set, we can find, we can remove, we can append. Adding space, again, we kind of know is slow. We get the length out. This one, does this matter how many items we have to get the length?
No.
No, there's no loop. It's all of 1. It's constant here. Initializing ourselves here. Sure, still constant, I guess. I don't usually look at inits for speed here, but why not? We could, right? It's still just 2 lines of code are always going to run. Same 2 lines of code every time. All right, so we've got our lists here. Now, I think we could figure out the size of our self here too, right? I think we can print the size of. I think that works. Maybe. Let's try it and see. So let's see if we can get the size of, let's do this one here, right? We appended it, and then we'll get the size of sequence. Size of sequence. See if we get anything back out here. I'm not sure if it's going to work or not. No, okay, so it's not. So why it doesn't look like it's getting any bigger is the sequence itself stores the reference to data. The size of the reference to data is always the same. The data itself is so much bigger, right? But the sequence itself, like the amount of memory it's storing never changes here. The thing that it's pointing at, the data that it's storing, that somewhere else in memory changes and gets bigger. But the sequence itself doesn't get any bigger, right? The thing it holds is getting bigger. The thing it points to is getting bigger here. So I think we could check the size of sequence dot data. Now, again, this is bad and it's warning us, hey, access to protected member. Python saying you're doing a bad thing, you're violating a warranty, right? You take off the sticker, warranty's void. You're not supposed to touch protected things, but Python says, sure, go for it. Have at it. Now that we can see gets bigger, right, as we do our doubling. Right? So started off at 104 for a while, we had room for 5, right? And then it had to get bigger, and then it had to get bigger, right? This should be around 20, it had to get bigger, then around 40 it had to get bigger. So we can see in ours it's actually doubling. Again, probably not as efficient. I would probably guarantee it's not as efficient as the Python one, because really smart people have looked at the Python list and said, yes, it's good. It's open source code. Smart people have worked on it and fixed it and made it good here. Whatever their math is for it, works out relatively well. So sure, so if we didn't have access to the append method that was built in and our fine folks in Python did, we could write our own. This data is always a fixed size, and when we need more space, we just double and shift everything over. That's sort of the whole theme of that one here. All right, let's take a look, see how we're doing here. That's the wrong Zybook, shoot. My favorite URLs or my history has not updated itself yet. Efficiency. Yeah, he goes right into case studies here and exercises. That's really fun. Insertion sort is kind of neat. We'll get to sorts later. I don't think that's super worth looking at right now because we'll spend more time looking at sorts later. It's just a type of sort you can do here. Yeah, the efficiency of Python sequence types. Here we go. So lists and tuples here. It gives you all this cool math here. So the index of value, right, k, where k is the, sure, he had some fancy math here, that's fine. Ooh, slicing, we didn't do slicing, that's fine. We didn't do comparisons of one sequence to another sequence here. It's probably not a big deal. To multiply, to append two together, yeah, that's okay. We did length, we did data. The count of something, we didn't do count of something, we could do that if we wanted to implement it, that's fine. Index of something, sure. Isn't this all fun? Yeah, inserts, pops, removes, deletes. Yeah, we did remove. Oven, yeah, I think that's all fine. And so I do like this versus the regular textbook because you get these cool illustrations that Zybook gives you. Again, just print it to a PDF to keep it for next semester so that you've got all of it if you do need to use the stuff for 350. Just make sure you go print your chapters as PDFs because you'll lose access to this, right? It's a subscription model, not a purchase model. But it's cheaper than the physical book was, which I thought was cool. So, or just Google, right? But again, I like when authors get some money for their effort. I don't care about the publishers too much, but the author, put some effort into it here. Yeah, Python strings, patterning, cool. I think that's pretty good for this. Wow, we had the whole week for that. you want to start early on stuff on Thursday, or do you want to take Thursday to work on the project that's coming up, or what do you want to do Thursday? Oh, no, I'm sorry, it's due Thursday. I'm so confused. Okay, so Thursday, my other class we're off a week. That's what I'm confused about here, I'm sorry. So Thursday then we'll go over the solution to Project Zero. Probably not actually a whole lot more we need to do for arrays and sequences, or array-based sequences. Check out the chapter, peruse through it. We'll use that as a launching point for the next topic, next chapter. So we build on them using these array-based sequences, which is kind of fun as we go. But yeah, so Project Zero, we got a little bit of time. If you got questions about it, let me know. We'll do that Thursday. I'll go over the solution in class. And then we have our next project, which is a recursive-based project that we'll talk about as well. So solution, and then project one that I'll assign. And we'll have 2 weeks for project one, right, which puts us out at, what day is that? 2/13, right, for that one. That should be pretty good. And then actually the next project will be based on stacks, queues, and decks, which will be fun. The last project is based on linked lists. So that one gets pushed a little bit off, but it's okay. We'll keep using those as we go a little bit later. So we've got 2:13 to 2:20. We have spring recess probably to like 3:05 then, and then 3:05 to 3:19 for that last project, and then 3:19 to 4:22 for the final project. We do have to do in pairs. That is a learning outcome that we work in pairs here, if I recall. We're assessing if you can actually do this as part of a team. So the individual is not an option for the final project, right? Because part of one of these things is we're learning to work with a partner, which actually makes more work, right, to be honest, because you have to spend time talking to each other, which is good though, because the way that you talk to each other is in English, in like design. Hey, I think this is a good approach here, kind of breaking things down into like a pseudocode level. We can draw some cute little pictures, do some UML stuff here. I think that's one of the outcomes too, right? Isn't it? Is it not UML? I thought we had it in here, maybe not. Maybe we can draw some cute little pictures and spend some time collaborating and thinking through your ideas before you just jump right into code will always save you time when it comes to writing the code. Because you've kind of thought through your model here. If you just start writing code and fumble your way through, you do like I do, you run into issues, and that's okay. But spending some time thinking about it will definitely save you some time. Awesome, yeah, so Thursday, project solution, next project, and we should be good to go. All right, awesome, thanks folks. I'll post this out on YouTube. You take care.